have power. Power? Yeah, the Philippines. Well, thanks everyone for actually hanging in here right through to the end of the day. I appreciate that, even though some people had really long days and are probably flagging by now. So I had a company in Sydney with about 50 staff in the banking industry decades ago, and software, so sort of worked with banks all over the world, replacing their dumb terminals in all their branches with smart PCs and other mini computers. And that was software. It was just straight software. Okay, so I had to run on a whole lot of different people's hardware, which was a bit of a mission. But it was still a fairly straightforward sort of software project. So I eventually sold out to a multinational and retired back to academia. And it's interesting doing AI because it's one thing to write some code to just get the results, to get a publication out, and just enough, it'll work just well enough for those results for your publication. If you sneeze, it'll break. And then it's quite another thing to get the AI working well enough that it can actually be useful to people. So all over the world, we see governments giving people like us at universities and research institutes funding to do cool stuff that they hope industry will take up. So here's what I've discovered, that you do it to tick the boxes that the government gave you, and again, as I say, it's just research code. If you sneeze, it'll break. But to actually be able to give it to a company, it would mean that company has to have all the capability your team has. And the other thing is, the only way to find out all the problems that that company is going to discover is to do hundreds and hundreds of field tests, especially if it involves robots and other things like that. And of course, there's not funding for commercialisation. None of these governments around the world give funding to commercialise it. It's just to do this proof of concept research. So that's been a really interesting journey to figure out how to do these hundreds and hundreds of field tests where you actually discover all those theoretical problems you have to solve to make this useful for industry. Because when you wrote the bid, you didn't really know enough about all the other problems that you might find. And the team, as I said, that's best suited to do that is the team that you've probably got assembled already. So the real challenge is trying to stretch the money we do get so we can, under the radar, do way more field tests, find out a lot more information. So here's just some examples of this, where we were, and it's interesting because, like, I started this one looking at vineyards about 15 years ago, big, huge caravan-sized thing we pushed through the vineyards with green screen behind on one side and cameras on the other and lighting. So in other words, I was so terrified of being outside in the real world with the computer vision AI that I took the lab with me into the vineyard with controlled lighting conditions. But now we have really good AI algorithms. So we've done it with NERF and Gaussian splatting and so on. And it has made a huge difference to actually being able to get enough points. And it's only taken me 15 years to finally start to crack this, to have enough points, like for canes are horrible. On vines, you get up to 7 canes overlapping in 1 point, and even humans have to shake them sometimes. But what I was really pleased about this, and I didn't realise until I saw the scan, is that I'd always joked with my teams, let's see if we can aim for 0.1 millimetre per pixel so we can really see the high detail in these plants and so on. And then when I saw the spider web, I thought, oh, hooray, we must be getting pretty close to 0.1 millimetre per pixel to see that. But when you think about what is a point cloud, it's just to a computer. Okay, it's brilliant to us. We cognitively interpret it and we go, wow, there's a vine and there's all the depth and there's all the, even a spider web. But to the computer, it's just a whole lot of random points. So at some point, we have to give meaning. So that means we have to figure out how to label all these points and say they all belong to that cane, and there's a node there, and there's a node there, and so on, and there's how long it is, and there's the dimensions of it. So at some point we have to do that, which is really challenging. So here's one where we're doing it over time. So every few weeks or so, we're just sort of scanning. Oops, sorry. We're just scanning the same vine, and you sort of see that first there's no berries there, and then some month or so later, then we actually see some berries appear, and then as time goes on, we see more and more grapes appearing. And what's interesting here was figuring out how to see all this information behind the leaves. So if I just pause this where it's found a whole lot of apples, and you imagine you've just put a GoPro on a tractor and you're driving past. There's so many apples, you won't see that one as an apple, you won't see that one. So we sort of cheated with a sledgehammer approach, having like 12 megapixel cameras, like 2 rows of 6 megapixels moving at a fast walking pace. So we're seeing an insane number of angles with hundreds and hundreds of images for each side. And that's just to get to step one, to get to the point cloud. And then once we've got a point cloud, we can label stuff, but hopefully we've captured the structure underneath this before we labelled it. So when we look at the complexity, there's the image acquisition. We keep spending so long on cameras and lenses and LEDs, and then finding reflection off the leaves interferes with the Gaussian splitting AI algorithms, and so we put polarizing filters on the LEDs, and it's astounding the first principles you have to do, even before you get to the whole point cloud and do the full structure from motion, as I just showed you. And then once you've got this perfect point cloud that's unambiguous and high enough resolution where you can see everything behind the leaves and so on, if we just want to do a plant without leaves on, then we've got to segment, well, what is the woody structure and so on. We've got to skeletonize it before we can even get to a model of it, because when us humans look at it, we just see a plant, we see there's some fruit, there's a leaf, there's a branch, we just automatically interpret that. But to get to that point where you actually have a real 3D model of it, where everything is labelled with metrics, which is what is needed out there, then it's just a whole nother order of magnitude. And every step of this path has to be so bulletproof, because you just scanned petabytes of data for a large vineyard. And when you talk with industry, they say, well, hang on a minute, petabytes of data, not sure if we can really store that and then process that. Can you do some data reduction on board? So as well as all the navigation you're doing with AI algorithms to know exactly where every plant is, you're now trying to do a whole lot of pre-processing on the edge, and then doing, to minimise the post-processing you're doing in the cloud and minimise the amount of data. So it's a really interesting challenge. And this code, for it to work, this whole pipeline has to be really bulletproof. Like usually you'll have, one student doing a bit on something, another student doing a bit on something, and there's no way their code can work together. So even the last year, we've been having regular meetings just to make code more commercialisable, quality, more bulletproof. So it's fascinating, the huge extra effort that needs to be done to end up with metrics, all the metrics and labelling of plants, so we can start automating in agriculture and aquaculture. Because without this, first of all, we can't automate what we can't see. So if the leaves are hiding a whole lot of things, we can't automate it, because you see all these YouTube videos with people harvesting apples, but if you're leaving 15% of the apples still on the trees, well, it's cheaper to use human labour, because you don't want to lose 15% of your crop. So we've still got a way to go to get this really, really robust, sufficiently robust that it'll work reliably day after day for industry. In windy conditions, like at the moment, the wind starts blowing all the leaves around, so you've got the leaves in one position, and then you take the next frame of cameras, the leaves are in a different position, and you're trying to figure out, well, is that the same leaf or not? So there's all these issues that come into this sort of thing. So it's similar things with drones using tools, where you're relying on improving how accurate they hover when they use tools, for pruning branches near power lines, pruning our pine forests in New Zealand, our third largest export industry. And it's another problem where I thought, oh, this will be easy, until I went and started pruning branches near power lines, and the wind's blowing them all over the place, faster than the drone can react to them. So then you have to do a whole lot of, predictive maths and get some AI involved and say, can we even predict somewhat where that branch might be based on the last few seconds of video and so on. So it's really interesting, the problems you end up with that you only discover once you have got a working prototype to show the industry partner that you're working with. And similarly, scanning scallop beds, where in New Zealand they're a bit different from Europe. They like to cover themselves with sand so you can't see them. So then you also need 3D information as well as 2D to try and see where those little where the mouth is on them. So that's been really interesting, and developing a robot arm. And another thing I've found is that when we start doing things like pruning grapevines or lifting scallops off the seabed, or trying to get a drone to prune, when we start doing manual labour tasks, suddenly those metrics become essential, that we've had a whole lifetime of understanding where the metrics are. And so that becomes about an order or two of magnitude to do this. So it's been really interesting going through this journey of getting these things to the point where we can commercialise them. So all of these, we've started companies and we are commercialising them, where we end up with all these metrics and information about these products. But it's also interesting commercialising, because it has to work well enough that when you demo it to industry, they're convinced that they could use it. They know that us universities will demo things and they break all the time. But if they really want to part with cold hard cash and get invested in what you're doing, they want to see it working. And that's where you need to put that extra time into doing those hundreds and hundreds of field tests to find all the other theoretical problems and solve them. And it's really nice. There's some really quite good funding to sort of move into startups like KiwiNet and also Royal University at Auckland, and Auckland has their own funding, and there's some really good funders available in New Zealand that are, some will fund you before you have any industry who are using your gear, and some will fund you after that. But there's some very good funding pathways for this type of thing. So, yeah, 15 minutes goes really fast, doesn't it? Yeah, so my advice, if you're wanting to commercialise, unfortunately you have to put that extra time in to make your code bulletproof. It's got to be really reliable. When you demo to people, you must demo to industry and show them lots of demos, get them working with you, and then look at all these funding pathways that exist to help with startups. So there's a lot, and your research office knows them all, and I've found research offices at universities really helpful and supportive for anyone who wants to get into startups. And let's face it, at the end of the day, it's really nice to feel that people might be actually using what we've been working on out in the real world. So that's probably it. I could talk for another 15 minutes, but I better stop there. Thank you.